Hello, Paul 251 students. We're now going to be talking through an example of using chi-square statistics for hypothesis testing. So imagine a researcher wants to know if there was a relationship between gender and vote choice in the 2016 presidential election. And the researcher is figuring this out using data with 200 observations. And for our purposes here, this is some fake data. I've changed around the numbers just to have things nice and round and evened out. So let's talk us through what this data look like in this cross-tabulation table. So here I have my gender variable. It has two categories, men and women. This row here is men. The second row here is women. We see we have a total of 92 men and a total of 108 women in our sample. I also here have three columns. Each column is representing one of the values of the vote choice variable. So we have three options here for vote choice: Clinton, Trump, or other. And again, this is a nominal variable. These are simply categories. There's no ranking or order to them. It's just three different choices of who someone could have voted for. And we also can see here some totals. So we have 94 people in our sample that voted for Clinton, 81 voted for Trump, and 25 voted for other. And here, this bottom right cell here with the number 200 is the total number of people in our sample altogether. So this is our N of 200. All right, so that's our setup, that's our data, and now we're gonna figure out if there's a relationship between gender and vote choice in the 2016 presidential election. And to do this, because we're comparing two nominal variables in a cross-tabulation situation, we're going to be using the chi-square statistic. And the logic of chi-square hypothesis testing is starting with a point of the null hypothesis. And this null hypothesis is saying that there's no difference between values of the dependent variable across groups in the population. So here, if our dependent variable is who you voted for in 2016, we have groups that are Clinton, Trump, and other. Well, our independent variable is gender. So if the null is true, there should be no difference in patterns of vote choice across men and women. Men should be just as likely to vote for Clinton, Hillary, and other as women are. And if we are observing any differences in vote choice on the basis of gender, these are simple chance variations that we're getting simply due to random sampling and random chance. So here our logic is that we have this chi-square statistic of 0. Our null hypothesis is 0, no relationship between the independent and dependent variables. There should be no differences in observed values across groups. In contrast, we'll have an alternative hypothesis. And this is a non-directional alternative hypothesis. It's simply saying that there is a difference between values of the dependent variable across our groups. So that means the pattern of voting for men should be different from the pattern of voting for women. Here, this means we have a chi-square statistic that is not going to be equal to 0. And again, plus random error, keeping in mind that if we're doing random sampling, we're always going to have some element of chance. Okay, so that's our setup. Now, a couple things to think about before we get into the mathematics of how to calculate a chi-square test. First is thinking about how the data vary across the two variables in the model. So here, when I talk about the row marginal, I'm talking about marginal differences between men and women in our sample. And if we go to this far right column, this total here, what this is showing us is the total of men versus the total number of women in our sample as a whole. And here we can see we have more women than men. We have 108 women compared to 92 men. So 54% of our sample, 108 over 200, 54% of our sample are women. So across the board, for each category of vote choice, we should see more women than men because women make up more of the sample. So that's our row marginal. That's the information we know being taken away from the fact that we have more women than men in our sample. Similarly, we have a marginal or difference across columns. So here, this bottom row with total shows us the total number of voters for each of our three choices. We see 94 for Clinton, 81 for Trump, 25 for other. So of these three, Clinton has the largest share of votes. That 94 out of 200 is 47%. So that difference needs to be baked in across the board. So when we're looking at the comparison of how men and women voted, we should always see 47% going to Clinton. Now, in a world where the null is true, any differences between men and women should be equal to 0 plus or minus random chance, which leads to a question that we need to answer before we can even start the statistical testing. And that is, what would the frequency of vote choice be in this table if the null were true? So in a world where differences between men and women are 0, if the pattern of voting for men is exactly the same as the pattern of voting for women, what numbers would we observe in these 6 cells? And that's step 1. We need to calculate what those expected frequencies are and then compare them to what we're actually observing in this data. So the steps to chi-square, and these are in a document posted on Blackboard called chi-square steps. These include the following. So first, we're going to calculate the expected frequency for each cell. This is going to be what number we would observe in each cell if the null hypothesis is true. So step 1 is we need to calculate that expected frequency. Next, we're going to subtract that expected frequency from the value we actually observe in the data, or the observed frequency. Then we're going to square that number, or they're going to divide that number by the expected frequency. We're going to sum up all those cell-by-cell calculations to get the chi-square test statistic. And here our null hypothesis is a chi-square test statistic of 0. So obviously we're going to be looking for a number that's going to be statistically larger than 0. We're going to have to figure out our degrees of freedom, just like we did for the t-distribution for chi-square. We're going to have to figure out some degrees of freedom. And then finally, we have to go to our handy-dandy chi-square lookup table to figure out what our test statistic is and compare our level of significance. So let's start, and I'm going to do this by concurrently having 2 things open. I'm going to have the slides open, and I'm going to have this document with my chi-square steps. So let's move this over here. Cool. So step 1 to our chi-square test is to calculate the expected frequency for each cell. What amount we should observe in each cell if the null hypothesis is true. And this is notated as F sub E. So the number of people who would be in each cell if the null were true. And again, keep in mind, this is if frequencies or if any kind of differences were occurring solely due to chance, and if there was no gender difference in how people voted. So logically here, if gender doesn't influence party vote choice, then the percent of women who vote for Clinton should be the same as the percentage of women who vote for Trump and or other. Now, keep in mind the actual frequencies might be slightly different here simply due to random chance. But let's walk through this logic a little more. So I said that 54% of my sample were women. That means of the people who voted for Clinton, 54% of them should be women as well. If I look at my Trump voters, 54% of them should be women as well. Same with other voters, 54% of them should be women. So based on that logic, I'm going to compute the frequency based on our totals. And this is our overall formula to do this. And this is also listed here in the steps to the chi-square. So to figure out the expected value for each cell, the F sub E, we have a column total times a row total in the numerator, and that's going to be divided by the grand total in the denominator. So that means we need to figure out and find row and column totals for our numerator, and then identify in our cross tabulation what that grand total is going to be. And then we need to do this calculation for each cell. And then I always like to double check to make sure the columns still add up to the overall total. So here I have this table where I have everything set up for us to do this step by step. So I'm actually going to also open up my calculator. So we have these few things open. Here our formula for doing the chi-square test is column total times row total over grand total. So let's start looking at men who voted for Hillary Clinton. So here our column total for men is 92. I'm going to multiply that by the, sorry, Claire, let's do that a different way. So let's start with column total. So we have, if we're looking at men who voted for Clinton, our column total for Clinton is 94. We're going to multiply that by the row total for men, which is 92. And then we're going to divide that by the grand total, which is always going to be in our bottom right-hand corner here, 200, the number of people in our sample. And that gets me 43.24. As you can see, I've already filled that number in. So just to maybe make it a little clearer for you, I can say we have 94 times 92 divided by 200, and that is equal to 42.24. Let's look at this for men who voted for Trump. So we're going to start by identifying our column total. That here is 81. We had 81 people who voted for Trump. We again have 92 men in the sample, and that is going to be divided by our grand total of 200. So keep in mind, for every single cell we're doing this calculation, the denominator is always going to be the same. The denominator is always going to be this grand total of 200. So I'll calculate it here, 81 times 92, that's equal to that number, divided by 200, 37.26, boom. And let's do the other category, and then you can take my word for some of the other stuff. So we have our column total here of 25, multiplied that by our row total of 92, divided by our grand total of 200. And if I go 25 times 92 divided by 200, that is not correct. So let's try again. 25 times 92 divided by 200. There we are, 11.5. Okay. So I do this for each of my 6 cells, 3 for men, 3 for women. And you'll just, let me just write out what this would be. So for women, our column total is 94. Our row total is 108 divided by 200. For women voting for Trump, that column total is 81 times 108 for our row total divided by our grand total of 200. And then finally for other, we have a column total of 25 times a row total of 108 divided by 200. Okay, so that is step 1. We have now calculated the expected frequency. So this is the amount, or this should be the raw number of people we would expect to see in each category if the null were true. So in a world where the null is true, there is no gender differences in vote patterns, we should see 43.24 men voting for Clinton and 50.76 women voting for Clinton. If the null hypothesis were true, that there are no gender differences in voting patterns, we would see 37.26 men voting for Trump and 43.74 women voting for Trump. Okay, so that's step 1. Step 2, we subtract the expected frequency from the observed frequency. So F sub 0 is the numbers we actually observed. We subtract from that F of B. I've already filled those in for you, so I'll do the first two just so you get a hang of the math that I'm doing here. So for men voting for Clinton, our observed is 41 and our expected is 43.24. That's negative 2.24. If I look at women voting for Clinton, my observed is 53, my expected is 50.76. That is positive 2.24. So as you're noticing here, these things are going to look like they're canceling out. So negative 2.24 plus 2.24 is 0. If I look at this for men who voted for Trump, my observed is 40, my expected is 37.26. That's 2.74. If I look at women voting for Trump, my observed is 41, my expected is 43.74. That leads to a difference of negative 2.74. Again, they would cancel each other out. So I've calculated this F sub 0 minus F sub E. I've done this 6 times. Now, as I've already pointed out, these numbers in some ways are mirrors of one another, one positive, one negative. So if I were to add all 6 of these values up, 2.24, negative 2.24, 2.74, negative 2.74, negative 0.05, 0.05. If I added all of those up, I would get 0 because all of the pluses and minuses are canceling each other out. So the way to solve that is to square that number. So that is step 3. Square this number for each cell. So basically I have that F sub 0 minus F sub E and I square it. So here I square negative 2.24, I get 5.0176. Funny thing, I also square 2.24 and I also get 5.0176. So in effect, squaring each of these numbers gets rid of the negative. And now I can actually start adding them up together so they don't cancel each other out. So that's step 3. I have filled all of those values in. Next, step 4. Divide that number, so divide that squared number by the expected frequency. So here's our formula, F sub 0 minus F sub E. Take that value, square it, then divide it by F sub E. So here, for instance, if I'm looking at men voting for Clinton, I have 5.0176. I divide that by 43.24. And I get, rounding to 3 decimal points, 0.116. I'll do this for women voting for Clinton to give you another example. So here I have 5.0176 divided by the 0.76. And again, rounding to 3 decimal points, I get 0.099. Okay, so I've done that for each of these 6 cells. And I get 6 values here that represent the observed minus expected frequency squared, then divided by the expected frequency. Next, I calculate my chi-square statistic. And the formula to calculate the chi-squared statistic is a summation of observed minus expected squared over expected. Well, if we ignore the summation sign for a sec, what's left here is observed minus expected squared over expected. Well, that's this red value in red in each of these 6 cells. So effectively, what our chi-square is the summation of each of these 6 values that we've calculated. So here I'm going to head back to my slides for a sec. So our chi-square test statistic is this summation of all of our observed minus expected squared divided by expected. It's simply adding up all of the cell values that we just calculated. So in this example, my chi-square is going to be that 0.116 plus 0.201 plus 0.22 plus 0.099, blah, 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 blah. Adding those 6 values up together, we get a chi-square of 0.629. So that is the chi-square value that we have calculated for this set of data. Our next step is to determine the number of degrees of freedom. Because just like our t-statistic, our chi-square also has different distributions depending on the number of observations in our sample. So overall, our formula to calculate degrees of freedom is the number of rows in our data minus 1, our number of columns minus 1. So in our example, we have, if we think about rows, this was our gender variable. So we had two values here. We had men and we had women. So 2 minus 1 is 1. Then if we think about number of columns, we had 3 different values of our vote choice variable, Clinton, Trump, and other. So here we have 3 minus 1 is 2. Now I want to go back up for a second because here's a commonly occurring mistake that people make. So you might have this cross tabulation table here, and you have your row for men, your row for women, your row for total. And then you have a column for Clinton, column for Trump, column for other, column for total. This column for total and row for total do not count towards the degrees of freedom. You're simply looking at the number of values in each variable. So when I talk about number of rows minus 1, I'm saying look at the variable in your rows and count the number of values. So it's gender, we have 1 for male, 2 for female. Here's our columns. We have 3 different options for vote choice, Clinton, Trump, and other. So that's one thing that people really get tripped up on. So when you're thinking about degrees of freedom and you're thinking number of rows, number of columns, don't literally count up the number of columns and number of rows in a crosstab. Just ask yourself, how many values are in your dependent variable? How many values are in the independent variable? Or how many values are in variable 1? How many values are in variable 2? Makes your world a lot easier. So we have now identified our calculated chi-square statistic. We have now identified our degrees of freedom. And again, to reiterate, understanding that these degrees of freedom are important is because just like with the t-distribution, chi-square has different distributions based on the number of observations or number of degrees of freedom we're dealing with. Okay, so there are many different chi-square distributions for many different sample sizes or ends, or for how many different categories we have across our independent and dependent variables. And this will be really important as we start to use our chi-square lookup table, because we're going to have to figure out what type of degrees of freedom we're using. And that leads us to step 7, the very last step where we are making the statistical inference. And to do this, what we want to do is compare the chi-square value that we calculated to the critical value of chi-square at the 0.05 level of significance, or that alpha of 0.05 level of significance. So what we're going to do, we have to figure out if the calculated chi-square exceeds or falls lower than the critical value of chi-square, where all 95% of cases would occur if the null is true. So to do this, I'm going to go here to Blackboard, go into our class, and then if we go into content and our week 13 materials, there is a file here called chi-square table. I'm going to click on that, and then I'm going to click on the link to open it up in a new tab. So with this chi-square distribution table, each column here represents a different value of alpha. So here, this column 0.05, I'd say when you download it, if you want to just highlight it or like put a star by it, do so. This is our alpha of 0.05. This is the column we're going to be looking at for the rest of the semester. So anytime I'm giving you a chi-square problem, I'm going to be asking you for the 95% confidence range. I'm going to be asking you about this alpha of 0.05. So you're always going to be looking in this column. So now the trick is to then find the value of chi-square that matches the degrees of freedom in this column of 0.05. So as we had already calculated, our degrees of freedom is 2. So we're looking at this row right here with 2 degrees of freedom. So 2 degrees of freedom, alpha of 0.05. We have a critical chi-square value of 5.99. So if I go back to my slides, if we're looking at this distribution here, and we have a critical value of 5.99, it would fall somewhere around here. Everything to the left of that would be where the null is true. Everything to the right of that would be where the null is false. So basically, we calculate our chi-square, we compare that to the critical value, and then ask ourselves, does it exceed the critical value where 95% of all cases occur? If it does, then we reject the null. So let's go back to the initial question. Is there a significant relationship between gender and 2016 vote choice? Why or why not? Well, let's see here. Let's look at a couple things. So we had our critical chi-square of 0.629. We also had, so we had our calculated chi-square of 0.629. We have our critical value of chi-square, which is 5.99. So if I go here, so if our calculated is 0.0629, our critical is 5.99. Well, we actually have a world now where our critical is greater than our calculated. Or another way to think about it, our calculated is less than our critical. Okay. So if our calculated exceeds the critical, we reject the null, otherwise we can't. We are in a world where our calculated is less than our critical, therefore we cannot reject the null. We fail to reject the null. There is no significant relationship between gender and vote choice. So no relationship, fail to reject the null. Okay. So that's our chi-square. That's how we do this. We have two nominal variables. We try to figure out if they're related to one another. We calculate a chi-square test statistic. We compare it to a critical value of chi-square. We see if the calculated is exceeding the critical. If it does, we reject the null. Otherwise, we fail to reject the null. A couple final thoughts that I have. So with chi-square, this is a really great tool for comparing two categorical variables and figuring out if things like gender do relate to vote choice. But the problem is twofold. So number one, these things are really sensitive to sample size. So the more people we have in our sample, the more likely we're going to have significant results for really small differences. So in this case, if I had, instead of 200 people in my sample, if I had, say, 2,000 or 20,000, I would have had a much larger chi-square, and I would have had most likely a significant difference or a significant dependency. The other problem with chi-square is that it really works in broad strokes. So what our results are telling us about the direction or the strength of the relationship isn't very much. It's basically saying these two things are related, but we don't know if it's men or it's women that vote more often for Clinton, or we don't know the magnitude of difference or the magnitude of the effect of how gender influences vote choice. We simply know that these two things are statistically significantly related to one another. And with that, that is chi-square. If you have any questions, shoot me an email and the practice will be up on Blackboard.